So I said it's an architectural design where roads are built tilted towards an angle to the center. An architectural design where roads are built Hey, where is architectural? So I'll give it to you last time. So let's continue. Architectural design where roads are built, okay, by tilting it at an angle towards the center. So either by tilting the road at an angle towards the center of the circle, towards the center of the road, or raising the outer end, or raising the outer end of the road. So if you have a curvy road, a banked road is like this. The road must be curvy. So roads are banked at areas where there is curvy curves. So the road is built in such a way that the outer end is raised towards an angle in a sense, so it creates a situation like this. So cars plowing on such road moves tilted. The cars are also tilted towards an angle. And it is there for safety purposes to prevent where the car can easily skid off the road. Okay. And when roads are tilted, it enables motorists to embark on a certain maximum allowable speed, which cannot be embarked on when the road is not banked. Okay. So when the road is banked, drivers do not usually depend on friction, especially when there is no friction. Drivers do not depend on friction to turn, meaning something else provides the centripetal force. We all know that the centripetal force is to be provided by friction when a car is negotiating a bend. But in some cases, there may not be frictional force on the surface. Yet the car can make that turn without depending on friction. So let's take this to be a banked road. The road is built and tilted at an angle towards the center, or its outer end is raised at a height h. This is a car moving on the banked road. My car looks more like the recent Pragia cars, but don't mind me. So this is it. Please, I don't know if you've gone through inclined plane. Have you done motion on an inclined plane?
Yes, please.
Because I'll borrow some concepts under motion on an inclined plane. So for motion on an inclined plane, yes, this is the weight of the car is always perpendicular to the ground, and this is the ground or the level ground. So this is mg of the car. Now on a flat road, when a body it lies flat on the ground, its weight is balanced by the reactional force, the normal reaction, and the moment the body lies on an inclined plane, the banked road is similar to an inclined plane. The normal reaction is always perpendicular to the surface on which the body lies. So we have this component as the normal reaction N. Okay, if we extend this reactional component, we have this angle between the weight and the normal reaction, the angle here equal to the angle of tilt. So if this is theta, this is also theta. Meaning if this value is 30 degrees, this will also be 30 degrees. Please, do you understand this? Do you understand how this works out?
Yes, please.
Yes, please.
Okay, then I can continue. Meaning that if I extend the weight vector up, I have this angle being equal to this angle. So if this is theta, by vertically opposite angle reasons, this will also be theta. So we have this normal reaction tilted at an angle. And so let's resolve. This is what we have. The normal reaction N acting at an angle to this theta. So let's resolve the normal reaction to obtain the vertical, the horizontal, and then the vertical component of it. What will be this component of the normal reaction? I want somebody to help me determine the horizontal component of the normal reaction. Anybody? Charlotte? Pardon? Amma?
N cos theta.
Good. So this component is n cos of theta. What about the vertical component? The vertical component.
N sine of theta.
So this component is also n sine theta. So it means when we resolve what we have here, we have this side giving us n cos theta, and this side which we want to bring onto the body or the car, okay, because of equal vectors, bring it here, n sine theta. So we have resolved the normal reaction into its vertical component, a horizontal component, and its vertical component. Please, is everybody in the building okay? Is everyone okay?
Yes,
Abba,
please.
Equia, Adoma, Amma, Asumani, Carl, Whistler, Lynn, Na, Ryan, Samuela, Stephanie, and Yaba. Please, are we all okay?
Yes,
with
please.
what we've done so far. Okay. All right. So if that is the case, when we look at vertical equilibrium, we have n cos theta component balanced by the weight of the car, mg. Then we have n sin theta component unbalanced. And by virtue of its direction, okay, there's the center of the band road curve. So we equate this to centripetal force mv squared over r. And so we realize that when the road is banked, the n sin theta component is equal to what provides, or is equal to the centripetal force that keeps the car within the curve. And this has nothing to do with friction. So it is the sign component of the normal reaction that provides the centripetal force on a banked road. So if you are asked what provides the centripetal force, okay, on a banked road, it is the n sin theta component of the normal reaction that provides it. So here, with this component, the car will be able to make the turn without depending on, okay, so with this component, of the normal reaction, the car would make the turn without depending on friction. Not necessarily depending on friction. The point is that we apply this concept on frictionless surfaces, especially where the road is so smooth after rainfall or snow, and motorists are to embark on a certain speed. When the road is banked, you could still make that turn without relying on friction. The point is that if you are embarking on that speed where the road is not banked, the driver can skid off the road and be involved in an accident. But where the road is banked, motorists could turn and move at a certain speed without necessarily depending on friction. So especially on icy road where friction is almost non-existent. Please, is that okay?
Yes, please.
All right. Now, looking at the two equations, there is a very important expression we can derive. When we divide equation 2 by 1, or divide equation 2 by equation 1, we have n sine theta component divided by n cos theta equal to mv squared over r divided by mg, or times 1 on mg. And so we have tan theta equal to v squared over rg. Therefore, v squared is equal to rg times tan theta. And this v is an expression we have seen under conical pendulum. V is equal to the square root of rg times tan of theta. And this gives us the expression for the maximum speed on a banked road, implying that the maximum safest speed to be moved on a banked road, the maximum safest speed to be moved, or the maximum safest speed on a banked road must be anything less or equal to square root of that. One is greater than this, the car skids. So the maximum speed depends on 1, square root of the radius, and also depends on the tangent of the angle of tilt. So this is the expression of maximum velocity on a banked road. And this one applies to when there is no friction. Okay. Now for motorists, when motorists are also negotiating a bend with a certain maximum speed, they also tilt. They tilt the motor through an angle. It's the same thing. They are also trying to take the bend by providing something extra, which would provide a centripetal force. And that is still the horizontal component, the vertical component of the normal reaction, n sine theta. So when they bend through the motor through the angle, it is the n sine theta which adds in our case, because we don't have icy road, we turn it to add up to the frictional force to enable the motorist to make the turn. And when the road is icy road, it is only the n sine theta that provides the centripetal force. Please, is that okay?
Yes, please.
All right. So if the maximum speed depends on the angle, square root of the tangent of the angle, then what it means is that there is a certain allowable speed for each banked angle, meaning when it is, assuming the angle is 30 degrees, the angle, the speed will be different from when the banking angle is 40, 45, 60. So each banking angle goes with a certain maximum speed. So when drivers are entering into banked road safety, in road safety application, there is that maximum speed to be embarked on such road. So they usually indicate the maximum speed here before you enter into the banked road. Maximum speed allowable here is equal to so and so. Those calculations are from what we've done. The V depends on the angle and then the radius. Please, any question? Because you are going to look at when there is friction on the road. So this is for frictionless road. Frictionless banked roads. So when it is frictionless, then the centripetal force is solely provided by the n sine theta component of the normal reaction. Let's look at when there is friction on the road. What happens? Egwe, are you done writing? Charlotte?
Yes, please.
Okay. Can I clean the board?
Yes, you may.
Pardon?
Yes, please.
As if Charlotte is the only one writing. What about the rest of you?
Yes, please.
Please, we're done writing.
Okay. So this one, frictionless banked road, the relation is the same as conical pendulum. And when motorists also make the bend, the relation is also the same as conical pendulum. Now, when there is friction, what happens? So when the road is banked and at the same time, there is friction on the road, how will this change? That is the next thing we are going to look at. So tighten your seat belts. Chris, are you there?
Yes, please.
Yes, sir.
Chris, there's no shortcut. So this is banked road. With friction. Friction between the tire and the road. So the road is banked, meaning tilted at an angle towards the center. Friction acts on the surface of the road. The weight of the car is always perpendicular to the ground on which the plane lies. So mg. The coefficient of static friction, which describes how rough or smooth the surface of the road is mu. The normal reaction, which is always perpendicular to the surface of the road, is here. Almost the same as what we just described. So N is here. When we resolve this, we have, this is theta, the banking angle is theta, theta. So this is also theta. So here we have N cos theta. Perpendicular to the plane, we have N sine theta component, which we just talked about. Okay, this is because that this component actually must be perpendicular to the horizontal component. It must be perpendicular to this one. So N sine theta. Now look at something. Centrifugal force tries to move the car from the circular path in this direction, and the frictional the centripetal force also tries to bring the car to the center of the circle in this direction. And once they balance, the car stays within, okay, the circular path. The frictional force is along the surface of the road. The friction is actually between the road and the tire. And it will also act to the center of the road so that it will keep the car within the circular path. But when we look at this, the frictional force, which is along the road surface, along the plane, isn't direct, it's at an angle to this one. Because it's along the road, it doesn't act directly perpendicular to this, but it acts at an angle theta. When you tilt the road by theta, then the frictional force would also act at an angle to this component by theta. So it actually depends on how the road is tilted. Please, is somebody okay here before I continue?
Yes, please.
Yes, please.
All right, let me change mine. Okay. So, because it's along the road surface, it also acts at an angle to this one. This component is supposed to be perpendicular to this one, but we see the frictional force tilting at an angle according to the angle of bend. So we have a situation of, maybe there's the reference line on which we have N cos, N sine theta. And the frictional force tilted at this angle. So we have a situation like this. F through an angle theta. It means that we can also resolve the frictional force F into components, right? We can equally resolve the frictional force F into components. And I want, help me determine the components of this one, of the friction, the horizontal component and then the vertical component. Yes, I'm representing what is here as this. this is tilted at an angle theta. Help me resolve F frictional force into components. Yes. The horizontal and then the vertical component. Aduma, Ekuya, Amma, Chrysler Lane. Yes. What will be the horizontal component of F with the angle? Chrysler, help me determine the horizontal component of F.
Mr. D, I don't get.
We have this, there's a reference. This force F is tilted at an angle like this by an angle theta. Once it is tilted, we can resolve this into vertical and horizontal component. Yaba? Yaba, go ahead.
Please, F cos theta over N sin theta.
So this component will be F cos theta. And then the vertical component here, which can also be brought here. Either we draw it here or here. It would also be F sin theta. Person, are you okay?
No, please. It's like you just labeled the one on top that it's N sin theta, and you're like, this one is
Yeah.
F cos theta.
Yeah.
I'm a bit
So
confused.
because the friction is tilted at an angle to this horizontal, the reason for which we are resolving it into horizontal and then vertical component. So it's like we also have F cos theta along this reference line, and we have this component, which we are also bringing along this component, along this vertical because of equal vector rule. So this is mg, but we equally have F sin theta along this component. So instead of bringing it here, I'm bringing it here because of equal vectors. Please, is everybody okay?
No, please.
Who isn't okay? Abba.
Mr. Idia.
Abba, you
Sir,
are
please,
not.
does it mean N sin theta is the same as F
No,
cos theta?
it's not the same. The N sin theta is coming in because of the fact that the road is banked. So because it is banked, we have the N vertical component of the normal reaction, N cos theta. Don't forget, it was here. N cos theta was here. N sin theta. But because of equal vectors, we are also bringing it here. Vectors are equal wherever they are if they have the same magnitude direction. So that's why we moved this from here to the body. So we are getting this component because of the banked road, and we are also having this because we are also considering frictional force of the frictional force between the road and then the tire. So they are all acting along the same direction. The reason for which I'm placing it on the N cos theta, N sin theta. Are you okay?
Sir, please, so is it like so the N is what you resolve to get the N sin theta and the N cos theta, and you do same for the F. So is it like they are imaginary lines? So
They are two things which occurs along the same direction. One is due to the angle, okay, due to the banking angle theta, and the other one is due to friction. N sin theta due to the banking angle theta, and F cos theta due to frictional force acting at an angle.
okay. Sir, please, I get it now.
Okay, Chrysler.
Mr. Asia, please. So,
Mhm.
do you mean we didn't indicate F on a frictionless because
Grace,
there's no
Grace, speak
friction
up.
at all?
Grace, speak up.
Did you, Mr. Asia, please? On
Mhm.
the when we're doing the frictionless bound,
Yes,
you didn't indicate F because there's no friction. So here,
exactly.
do you mean because
So, Chrysler, it's because when we were looking at frictionless surface, we didn't talk about friction. Don't forget, I said that applies on icy roads. When it is snowy, friction is eliminated. So, on the, are you okay? On the bank road, it is just the n sine theta component that provides friction. Here we are talking about in our situation, when the road is banked, we wouldn't have a situation of frictionless surface. Are you okay?
yes?
Okay. Yaba, your hand is up. Okay. All right. So when there's friction, friction is divided into component F cos theta, F sine theta. Okay. And the root is also banked. So we still have N sine theta component of the normal reaction and N cos theta component of the normal reaction. Okay. Now we are almost concluding. These are the key facts. Now let's look at vertical equilibrium again. By vertical equilibrium, we see n cos theta balanced by f sine theta and mg. This is equation 1. If you look at horizontal equilibrium, you have total forces acting horizontally. We have n cos theta, n sine theta plus f cos theta being unbalanced. There is no balancer at the other end. And so, because of their direction towards the center of this heavy road, we equate this to hello. Hello. Hello, can you hear me?
Yes, please.
Okay, I had this technical. All right, so we have these two equations. Now, frictional force is given by mu times the normal reaction. So let's substitute mu n into each of these equations. So n cos theta is equal to mu. Okay, let's even subtract. Let's transfer this to the other side. Mu minus mu n sine theta is equal to mg. I'm just transferring f sine theta to the other side of the equation so that we can factorize out n. We have cos theta minus mu sine theta equal to mg. Are we okay here? Hello, are we fine with equation 3?
Yes, please.
Good. Let's also modify equation 2. We have n sine theta plus mu n cos theta equal to mv squared over r. We can pull out n so that we have sine theta plus mu cos theta equal to mv squared on r, equation 4. Now what we'll do is that let's divide equation equation 4 by equation 3. So divide equation 4 by 3. Okay, so we have the n will cancel out when we divide. So we have sine theta plus mu cos theta over cos theta minus mu sine theta, which is equal to mv squared over r divided by equation 3. So times 1 over mg. Therefore, this m. We just want to create an identity. Please do not panic. We just want to create an identity. Okay. Now, the next step is that divide the left-hand side through by cos theta. So at the left-hand side equation, we are going to divide both the numerator and denominator by cos theta. Okay, and dividing through by the numerator and denominator implies as if we haven't done anything to the left-hand side equation. Please, are we okay? Are we fine? So
Yes,
sine theta divided by cos theta plus mu cos theta divided by another cos theta, all divided by cos theta over cos theta minus mu sine theta over cos theta is equal to v squared over rg. Please, we are multiplying this only by the left-hand side. The reason for which we are dividing through by the numerator and denominator so that it will look as if we haven't done anything. And actually, that's what happens. When we do that, the numerator, we have sine theta over cos theta, we have tan theta plus mu, because this is 1. Then this is also divided by 1 minus mu tan theta, which is equal to v squared over rg. We are only deriving an expression, so do not panic. Therefore, if you make v squared a subject, you have v squared equal to rg times mu plus tan theta over 1 minus mu times tan theta. So that when we take the square root of both sides, we have v max equal to the
Sir,
square
please, your
root.
video is glitching.
Pardon? Pardon?
It's glitching. I can't see. It's glitching.
Really? I'll bring it. Okay, I'll bring it up for you
Yes,
to
sir.
see. So finally, we have v max equal to rg times mu plus tan theta over 1 minus mu times tan theta. This is the expression for the maximum velocity when we are considering both friction and the banking angle, theta. Priscilla. Hello.
Deja.
I hope it's cool.
Deja, just go back. I'm having a network issue.
I'm coming. So let me write the expression up for those of you who cannot see properly. So V max is equal to square root of RG.
It's still the same.
It's still the same. Okay, I think I need to bring it down. The value is the same.
No, I think the screen is not clear. It's
I understand. Don't explain. So maximum velocity will be equal to RG times mu plus tan theta over 1 minus mu tan theta So this is the expression for maximum velocity when we are considering friction plus banked angle. When we are looking at friction plus banked angle, and then frictionless surface, we only had V max equal to square root of RG times tan theta. There's the difference between the two. For friction plus bank angle, and then for frictionless surface. The good news is that, in fact, most often questions are around frictionless surface. Frictionless surface. That's one. But the point is that you wouldn't know when somebody can decide to test you on when there is friction, when the road is banked. Any question? So here you could see that the maximum velocity or speed depends on both friction the radius of the curvy rod or the radius of the circle and the banking angle theta. For frictionless surface, the maximum speed depends on radius of the curve and then the bank angle without friction. Please, are we okay?
Yes,
So
please.
so when a motorist turns a bend, those motor riders, when they turn a bend, when the road is banked and there is a consideration for friction, if the two persist, consult this formula. When the two expressions persist, you must consult this. Then if it's only about bank angle, you consult this for both cars and motorists. And I will send you questions to this effect today. So we'll know how to apply these two different relations. Is that okay? Let me see if we have one quickly, because we'll look at right after this. Our next study is to start SHM. So let me see if I can get similar question for you on bank road. Already, okay. An example: a highway curve. A highway curve of radius 70 meters. A highway curve of radius 70 meters is banked at an angle of 15 degrees. Is banked at an angle of 15 degree, 15 degree.
Is of radius.
70 meter, 70. Is banked at an angle of 15 degree. At what maximum speed can a car take this curve? At what maximum speed can a car take this curve without depending on friction? At what maximum speed can a car take this curve without depending on friction? Take gravity to be 10 meters per second squared. A simple question. At what maximum speed can a car take this curve without depending on friction? Take gravity to be 10 meters per second squared. So make me proud. So it's clear without depending on friction.
Mr. Ija.
Hello.
Mr. Ija, please, I didn't hear the question. Like, I'm having network issues, so it keeps on breaking.
So do I take a shot and then drop it within the group?
Yes.
Will that help, Crystal?
Yes. Yes, please.
Okay. But I'm sure somebody is true. Charlotte, are you true? Amma, are you true? Lynn, Stephanie.
Sir, please, can you say the last part of the question again? The last part.
So said, at what maximum speed can a car take this curve without depending on friction? At what maximum speed can a car take this curve without depending on friction? Take G to be equal
Let
to
me-
10. Are you okay? Ryan,
Take G to be equal to.
10 meters per second squared.
Okay, sir.
Chrysler, Chrysler,
Yes, please.
I've just dropped it.
Yep, yep. Thank you.
Okay. Lynn, finished. Hello, Lynn. Oh, Lynn is gone. Am I finished?
Yes, please.
Akuya, Adoma, Samuela,
Yes, sir.
finished.
Yes, please.
Yaba.
Yes, please.
So did you get 13.69 meter per second?
Yes, sir.
That's the answer.
Yes, sir.
So this is a typical application of when there's no dependence on friction or when there's no friction. Okay, I'll send you examples on when there is friction and the road is banned. Okay, simple. If you have any question, please ask. If you have any question, ask before we continue. If you don't have any,
Sir,
Herbert. Yeah.
sir, please, the question that you gave us,
Mhm.
say the formula we use, but we use the frictionless surface to work it.
Exactly.
And so when I use the frictionless surface to work it and I input my distance, the calculator wasn't giving me an answer.
Okay, let's see. It's maybe, I don't know if your calculator's angular measurement is in radian. If it's not in degrees, it can affect your results. But let's see.
Okay.
So without depending on friction. So if we are not dependent on friction, then the radius is 70 meters and the angle is 15. So R equals 70, theta is 15 degree. What else do we have? We also have J to be 10 meters per second squared. So the maximum speed without depending on friction will be this, so that we have 70 by 10 times tan of 15. But as I said, in computing this, you must ensure that your calculator angular measurement is on degree. Because if it's on radian, it will affect your results.
Okay, sir, please, I was able to set it. I had 13.6
That's
meters per second.
that's the answer.
Yeah.
Please, sometimes you can also be asked to find the value of the normal reaction. Don't forget, we obtain this expression after considering n sine theta equal to mv squared on r and n cos. Herbert, mute yourself. And n cos theta equal to mg. So we divided and then got tan theta equal to v squared on rg, out of which we made v. So you can also be asked a question on calculating the normal reaction n, or even theta, the angle of tilt. Okay. Then another important thing that can also be asked. You see, on an inclined plane, as an inclined plane, when the road is banked, we have this banking angle theta, the height, and all that. And then the width, maybe the width of the road. Okay. Don't forget, you can also indicate that sine theta is equal to the height of the road, vertical height, h over the width of the road, or the length, which is L. So I've seen some questions also demanding the vertical height through which the road is raised and all that. So in such a situation, this length of the road or the width of the road will be given h, and you use that too. So take note of questions of this nature too. Please, is that clear?
Yes, sir.
Okay. Simple harmonic motion, SHM. Simple harmonic motion, SHM. Simple harmonic motion. When a motion is said to be simple harmonic, what does it mean? This kind of motion actually comes from, there is a meaning for each one. The word simple has its meaning to the motion. Then harmonic also has its meaning. As for motion, we all know it's a movement. Okay, so we understand. But the concept of simple harmonic motion comes from the major set periodic motion. Periodic motion. Then from periodic motion, we can talk about oscillatory motion. Oscillatory motion. Then finally, we zero in on simple harmonic motion. So let's understand each of the concepts. What is periodic motion? The word period in physics denotes time. Okay, so when we talk about periodic motion, we are talking about any motion that occurs within a specific time interval. So any motion that takes place within a specific where is the motion? Any motion that takes place within a specific time interval. Periodic motion. Another attribute of periodic motion is that this motion occurs at the same distance or displacement each time. And it is also repetitive. Also a repetitive example. We are told that the earth revolves the sun. Revolves around the sun. And it takes the earth. How many days does the earth take to make one complete revolution around the sun? Do I have people in the building? Hello. Or everybody is gone?
Oh, please.
How many days does it take the Earth to make one complete revolution around the sun?
365 days.
Good. So the Earth starts its journey from here. On and on and on and on. After 365 days, it has completed its journey around the sun. Then it starts again. Another 365 days. So each complete movement or rotation takes place within a fixed time interval, 365 days. After every complete revolution, the same path is taken again till it ends. So it is showing an attribute of this motion occurs at the same distance or displacement each time, each fixed time. And then the motion is repeated. So the motion of the Earth around the sun is an example of periodic motion. By this example, I want somebody to also give me another example. Any motion that is periodic. Somebody else to give me an example of periodic motion. Let me go to Stephanie. Stephanie, give me an example of motion that is periodic. We have called Stephanie. Okay, Herbert.
Sir, please, a bouncing ball.
A bouncing ball. Okay. A bouncing ball. Thank you. Stephanie, are you there? Okay.
So please, what about the swinging of the pendulum ball?
Exactly. Swinging of the pendulum ball. Okay, it takes a first time, which is for every complete revolution. And the motion is repeated. Abba.
Sir, please, I was going to say the hand of a clock.
Exactly. The hour hand, the minute hand, the second hand, all exhibits periodic motion. So please put the examples down. Amma,
Sir, please, the motion of a car wiper.
the motion of a car wiper. Yes. Equia, Charlotte. Akusia, rather. Akusia. Okay. So these are examples of periodic motion. Any motion that takes place within a fixed time interval is periodic. And you have mentioned several examples. Okay. Now let's go to another subset, which is oscillatory motion. What is oscillatory motion? Oscillatory motion. Oscillatory motion. Now, if you take a simple pendulum, and a simple pendulum is just a massless or weightless string. So from this point to this point is a string or thread. Attached to this weightless, we mean that its mass is very, very small. Attached to this is a mass. It's a mass. It's a mass. Please let me pick this call and then get back to you. So a simple pendulum is just when you attach a massless string to a weightless string, and then you attach a mass, a fixed mass. In position is the fixed point, or the axis around which rotation will take place. And then you displace the the mass in one direction. So I give it a small angular displacement, theta. This mass would move from the mean point. This point, the reference starting point, is known as the mean point. The mean point. So when you displace it, it moves from here to here. Then from here to this place. Because it has that momentum, mass times velocity, it crosses its mean point and then comes to the other extreme. Comes to the other extreme. Then moves from here to here. Process, so it is 2 from, 2 from, 2 from, 2 from here to here, 2 from, okay? So this is simple pendulum, okay? So the motion of a simple pendulum shows oscillatory kind of motion. Seesaw, somebody sits within the swing or swing, push, and the person will be moving to from, that repeatedly. Okay, so we define oscillatory motion as this. It is the repeated to and fro. That the to and fro thing is from here. To from. Okay, the repeated to and fro motion. Of a body around a fixed point. A fixed point. And the fixed point is the mean point. So this repeated to and fro motion of the body around a must take place around a fixed point. Please, is somebody in the building? Are you there?
Yes, sir.
Oh, so the repeated to and fro, or either to and fro or up and down. I wish I have my staffs here to demonstrate the up and down one to you. Okay, I'll bring something. A gadget to demonstrate next time. So it is either a to and fro or up and down. I have a spring here. I don't have a mass. That's my, okay. I'll bring a mass and demonstrate it in our next meeting. So either you define it as the repeated to and fro or up and down, up and down motion of a body around a fixed point. And the fixed point, as I said, is the mean point, also said to be the equilibrium position. So the same point, we term it as the mean point, fixed point, or equilibrium position. Okay, so the motion must occur repeatedly around a fixed point or mean point or around equilibrium position. Examples of motions that are oscillatory. Yes, let's list some examples of oscillatory motion. So examples of oscillatory motion. Yes, I think everybody should give me one. One, starting from Ryan.
So I don't know what it's called, but you can see the grandfather's clock. There's
Yes.
something that moves left and right. Yeah. Is
It's
that an
also
example?
it's also a pendulum. It's also a simple
Okay.
pendulum. Okay, so the motion of a simple pendulum. Two. Yes. Really bring your example before I call you. Two. Okay. Okay. Samuela.
Says spring.
Samuela, you must qualify it. Because you must qualify it because of this. I have a spring here. And I'm going to show to you whether it is exhibiting. Samuela, this is a spring. This is a spring. As it stands, is it exhibiting simple harmonic motion, Samuela?
Say no.
So qualify it.
Say the motion of a compressed or stretched spring.
So good. It would exhibit SHM when it is loaded or weighted. By it's being loaded or weighted means that you are suspending a load onto it. So when you suspend a load and then displace it, then it will show the repeated up and down motion. Okay, so the motion of a loaded or weighted spring. In the same way, I can't talk about simple pendulum because if the pendulum is not in motion, it doesn't describe oscillatory motion. Abba, you've waited on the line for so long. Come. You called
Sir,
in.
please, swing.
Pardon?
Sir, please, a swing.
How about I won't swing this? Qualify it.
A swing.
How about I won't swing it? Qualify it.
Sir, please. Sir, okay. The motion of a weighted swing.
So the motion of a swing, okay, the motion of a loaded or a swing. But if it doesn't move, it won't describe that. Stephanie,
Sir, please, the swinging of a door.
exactly. So, the swinging of a door. Yes. Ama,
Sir, please, the flapping of wings
the
of birds. Flapping of wings.
clapping of
Birds when they fly, when they flap their wings.
hey, hey, really, really. Yes, it describes that repeated motion, but there are lots to mention. Okay, so let me add Yaba and Lynn. Lynn, are you there? Oh, some of you do not, as many, you
Yes,
don't,
please.
as many you don't talk. Ekwiadoma, that's a move. Ekwiadoma, you don't talk. You're about it. Eh? Okay, as many. I'm again. Okay, so let me give you more. The motion of liquid in a U-tube, U-shaped tube. Oh, please. I'm not talking about the social media YouTube. It's like a test tube, but this is shaped like a U, the letter U. When you put liquid within and then you swing it, it will be moving up and down. 6, the motion of a loaded test tube placed in water or immersed or suspended in water. 7, the motion of a compound pendulum. We have a compound pendulum too.
And sir,
Hello.
sir, please, can you also say the motion of like your heartbeat?
That is repeated,
Okay.
but the timing, I can't tell because this repetition must occur within the same time. So it can be true. It can be true. Okay. Then the motion of the pistons in an automobile car engine, I mean. We have a lot of examples. The motion of electrons the motion of electrons in a conductor. Formation of current. There are lots of examples which we can talk about in simple harmonic or in a simple harmonic or oscillatory kind of motion. Okay. Now let's look at the big man or the younger or the youngest of them all, which is simple harmonic motion. Simple harmonic motion. Do I clean it?
Yes, please.
Simple harmonic motion. Now, simple harmonic motion is a special type of oscillatory motion or a subset of oscillatory motion. It's actually a subset of oscillatory motion.
Oh, Mr. Dear,
Mr. Kuya,
you have cleaned all the examples.
oh, but I asked you. Anyway, I'll give you video.
Of
I'll give you video, so don't worry.
yes, please.
Now, we define simple harmonic motion. It has some attributes of oscillatory motion, even periodic motion and oscillatory motion. But this one also has some added qualities or features, which makes it special. Okay. What is this speciality about simple harmonic motion? Yes, it is the motion of a body, or it is the repeated motion to and fro or up and down motion of a body around a fixed point. And by this, it shows the resemblance of oscillatory motion. So there's some element of that. Now, what is the added quality? The added quality is that for simple harmonic motion, I want to do something to demonstrate what I want to tell you. So give me a minute for my TLM. You just develop a TLM for this. Good. Look at this thing. When I give it a small angle displacement and leave it, it shows that repeated to and fro motion. Okay, so it is oscillating. All right. Now this oscillation, moving the body from its mean point. There's the mean point, there's the support. This point is the mean point of the body, or fixed point, or equilibrium position. When I give it that small angular displacement, theta and leave it, it has to oscillate about, move to and fro about it. Now, moving it from its mean point to any new position from 1 to this distance is what we call as the displacement. So this distance from 1 to 2 is the displacement. So the displacement of a body executing SHM is any distance of the body from the mean point or from the equilibrium position. Okay, so the displacement is any distance of the body away from the equilibrium position or the mean point. So when you give it a displacement in one direction and you leave it, it will accelerate in the opposite direction. So I move it, displace it to this direction. When I leave it, it would accelerate or increase its speed in the opposite direction. When I displace it here and leave it, it would accelerate in the opposite direction. 2. So we realize that for simple harmonic motion, the displacement is opposite to the acceleration. You displace it in one direction. Poof, my earpiece. I'm coming. Okay, so I will be doing the talking. Because when you speak, it will be faint. So you displace it in one direction and leave it, it accelerates in the opposite direction. The acceleration is when it is coming from the extreme end where you displace to and it's coming back, its speed increases with time. So it accelerates in the opposite direction. So if the displacement is y, then the acceleration a, because they have opposing direction, y is positive, a, which is the acceleration, is negative, or vice versa. 2, the other feature is that when you give it small displacement, it would also give you small acceleration in the opposite direction. So when I move it small and leave it, it will move in the opposite direction also small. When I increase the displacement very large, let me bring it here. So small displacement, small acceleration in the opposite direction. Large displacement, large acceleration in the opposite direction. Okay. So just small displacement, small acceleration. Large displacement, large acceleration in the opposite direction. And so we realize that it has 2 key features. 1, displacement is directly proportional to acceleration. When displacement increases, acceleration would also increase. 2, the displacement is opposite to the acceleration. Okay, so these are the 2 key features of a body exhibiting simple harmonic motion. So let's look at the definition of simple harmonic motion. We define this as the repeated to and fro, or up and down. Instead of to and fro, you can also use up and down. Motion of a body around a fixed point then, so this exhibits the features of oscillatory motion, but you are coming to talk about its key features or characteristics whose acceleration is directly proportional to the displacement. But oppositely directed. So the repeated to and fro or up and down motion of a body around a fixed point whose acceleration is directly proportional to the displacement but oppositely directed. Here you want to say that the displacement and then the acceleration are oppositely directed. So mathematically, this is the equation for simple harmonic motion. Acceleration A is directly proportional to displacement. Often the displacement can be y or x, y, but they are oppositely directed. And so A is directly proportional to minus y. This is Ama.
Sir, please, so can we
Ama,
say
speak
that?
up.
Sir, please, so can we say that simple harmonic motion
Ama, are you talking?
follows, it obeys? Yes, please. Hello.
Ama, I can't hear you.
Oh. What's my pen?
So
I
that
can't
is
hear me.
simple harmonic motion, SHM. Let me see if my earpiece can work for a while.
Sir, please, I can't see the board.
Hello? Ama.
Hi.
Hi. Ama, what was
Sir,
it?
can you hear me?
Pardon?
Please, can you hear me now?
Yes, I can.
Sir, please, I was saying, can we say simple harmonic motion obeys Newton's third law?
Yes. Yes. We'll come to all those attributes. So this is the key features of SHM. Okay. All right. So, and to let's end here since I have an issue with the earpiece. Okay, we have about 8 minutes to go. I'll send you your questions as usual. All right, so this is where we'll end today's lesson. We'll continue. Your questions will come and we'll have another session on Friday. Please, if you have any question, quickly ask. Lane be talking. As many be talking. Ekwiadoma be talking. Let's share our views
Yes.
whenever, we have a session. Okay. All right, please.
Yes.
Bye-bye and take care of yourselves. If you have any challenge, you can WhatsApp it to me, please. Okay. All right. Bye-bye to all of you.